Hello students, good morning all of you. Today in our video I want to explain electrostatic potential and capacitance. Okay, this is our chapter today. In previous we are discussing all the kinematics problems very well. Okay, so let us see all of them and practice. Good. Okay, in previous we had completed our electric charges and fields, the complete chapter in one shot video. But today we are starting with going to be learn electrostatic potential and capacitance. Okay, let us start our topic. Before going to that, you have to subscribe our channel and like, share to your friends. Okay, thank you. Electrostatic potential. So here in this we need to learn about the capacitance also. Capacitance. Okay. So capacitance is the different category you have to learn. Before going to that, you have to learn electrostatic potential here. Right. In our previous knowledge, we have discussed very well the Coulombs inverse square law. So if any two charges are separated in a small distance, these are the two charges Q1, Q2 are separated in a small distance, there may be a opposite or force of attraction or force of repulsion will be acting between them. If there is two equal charges, then the repulsion force will be acting. If two are opposite charges, then the force of attraction will be acting. This force of attraction or repulsion by the Coulombs inverse square law, we can write that is nothing but F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So this is the force acting between any two charges in a R distance. So this is the force acting between two charges in a R distance. And one more you have to learn, already we learned that electric field. So what is meant by electric field? Electric field, it is nothing but force acting per, so this can be denoted by the letter E. This is the force acting per unit charge. Force acting per unit charge or force experienced on the unit charge or the test charge. So that is the E is equal to F by Q. E is equal to F by Q. The force will be here, EQ should be acting in the electric field. And here we can write that E is equal to, where F is equal to, already you know that 1 by 4 pi epsilon naught, where Q naught something, whatever two charges are R square, it is F by Q, it is equal to 1 by Q. So from this we can write F is equal to 1 by 4 pi Q naught by R square, by Q it is equal, here we have to write. So then E is equal to 1 by 4 pi epsilon naught Q naught by R square. So this is the intensity of electric field on a point charge. Intensity of electric field. This is the force acting between two charges. This is the force acting on a charge. Force per unit charge. Force on a charge. Okay. So that is the intensity of electric field. So the variation it is that here there are two charges are there, but here the force will be acting on the another charge. So that is the intensity of electric field. Okay. Now we need to find we have to learn about the electrostatic potential. So how we define the electrostatic potential? So electrostatic potential is nothing but, in your dynamics you have to learn the external work done. So how we can find the work done in the dynamics? In electrostatic, we have to find the work done, that is nothing but potential. Okay, that is the potential. Now we have to derive the potential equation of the potential for a test charge. We have to derive the equation for the potential on a point charge. Okay, let us see how we can derive it. So these are the basics for the to learn this chapter. Okay, so now we have to learn about the electrostatic potential. It is electric potential. It is nothing but electric potential. Electric potential. So it is denoted by the letter V. Electric potential. Electric potential, it is nothing but the work done to bring the point charge. The work done to bring the point charge from infinitive distance to into the electric field. Into the electric field, and the work done should be here acting against to the field. Against to the field. So for example, here what I am saying it is the electric potential is defined. The work done to bring a unit positive charge from infinitive distance to into an electric field. This is called electric potential. Okay, electric potential V. Here the work done should be against to the field acting on a charge. Very important this point. Field acting on a charge. Okay. For example, let us take in a point charge. So this is a charge. We have to take in at point O. This charge consisting electric field around of it. So this is the, let it assume there is an electric field acting around of the charge. Okay. If there is another charge is there, point test charge, here at infinitive distance from this point to this point, there is the distance. It is how much distance here? Infinitive distance. This charge it is for example, here there is a charge Q, here there is a charge Q naught. This Q naught charge should be bring into electric field. The work done to bring the unit test charge from infinitive distance to into the electric field. Up to not from not here. So the test charge will be bring into the field. Whatever the point it is, we have to bring into the field. Whenever we have to take this charge from this distance in this direction, here outside of this field there is no force acting on that. There is no intensity of electric field. Okay, because of the field should be acting up to this range. Out of this range there is no force acting. So we have to easily move the point test charge, that is Q naught, outside of the field from up to here. Whenever we have to bring this point from O to something like that, here we have to say P. O to P is whatever the point it is from the distance of x distance to the field. Now we want to move into the field. So here there is some forces will be acting on that. Now the charge it is here. Okay. So now these two charges are separated in a small distance. Obviously, that is the distance, it is equal to x. Our aim is the unit positive charge is bring into the field, not to the up to the field. Okay, the electric charge is moves into the bringing from the infinite distance and into the field. Okay, so now the work done should be slow down because of the force will be acting on this charge. Because of this is the field. The intensity of electric field should be acting on that charge. It will be opposite. This is the intensity of electric field in this direction. But we have to we want to move into the field in this direction. So both directions are opposite. Then hence we need to work more. We need to work more to enter into the field. That's it. So that's why. So for example, we need to move from this point from P to whatever that is point A, which is the distance from the O to A, it is equal to R. We need to go from infinite distance to R distance. We need to go infinite distance to R distance. R distance is the point which is in the electric field. Infinite distance is the point which is outside of the field. Our aim it is the work done to bring a unit positive charge from infinite distance to into an electric field. Infinite distance to into an electric field. That's it. Not up to the field, into the field. How much distance into the field? That is R. From where we have to bring the charge? Infinite. Okay. Now the work done should be, we have to separate it in the equal parts. Some work done should be done here, that is dW work done. So if you have to integrate here, then you can get the total work done. Okay, for the equation of F into S, that is F into dx. So we have to integrate, we will get the what is that? Electric potential. The work done should be given to us. So here the work done, the electric potential, it is nothing but electric potential V is equal W by Q naught. Work done on a unit positive charge, that is W is equal, V is equal W by Q or Q naught. So here we have to bring in the charge Q naught, let it be here Q naught. If there is a Q, it is Q. If there is a Q1, it is Q1, whatever that is. So there work done, it is nothing but V into Q naught. V into Q naught. Okay, V into Q naught. So we need to find the electric potential. It is W by Q naught. The work done per the unit positive charge. Work done per the unit positive charge. That is the electric potential. We find the unit work done and divided by the charge, we will get the electric potential. Hence, we have to find the work done. Okay, clear? This is the electric potential. Electric potential. So here, the work done to bringing the unit positive charge from infinite distance into an electric field. This is called electric potential, and here the work done should be acts against to the field. Outside of the field there is no force will be acting on the charge. Hence we can easily move. But whenever we have to bringing the charge nearer to the field, boundaries of the field, then there is some forces will be acting opposite the motion. Hence, we need to go with more force because of they are opposite to each other. So this is the intensity of electric field and this is our motion. Okay, so hence there is a repulsion forces or opposite forces will be acting. We need to work done more efficiently, right? So this is the electric potential. Now we have to find the equation or derivation for the electric potential at a point charge. Let us see how we can derive it. Okay, right. So potential, the units of the electric potential, it is equal W by Q, nothing but W it is equal to joules and Q it is equal to Coulomb. Charge it is the Coulomb. Joule per Coulomb. Electric potential units are joule per Coulomb. Okay. So let us see how we can derive the equation for the electric potential. Derivation for electric potential at a point charge. Point charge. Now let us see derivation for electric potential at a point charge. Point charge. Right? Okay. So here we have to assume, so a point charge which is at point O, the charge Q is at point O, you have to assume the electric field will be acting around of the point charge. Okay. So now we need to bring the charge which is Q naught from the infinitive distance. So this is the infinitive distance. So we have to move in this direction. This is the intensity of electric field, you have to remember here. The direction of the intensity of electric field. So whenever we have to bring the unit positive charge Q naught from the O to X distance, so here Q naught is there. If these two charges are acting separated in a small distance, then there will be force will be acting, that is F is equal to 1 by 4 pi epsilon naught Q naught by what is that, X square, where in the distance it is equal X square. So this force it is the Coulomb force acting between these two charges. Right? Now we need to bring this charge into the field at point A, which is distance from the center of the charge, it is equal to R distance. Okay? So now our aim is the unit positive charge which is at infinitive distance is bringing into the field which is at R distance. So now our aim it is the unit positive charge which is at infinitive distance is bringing into the electric field which is at R distance. Okay. So now we need to move the distance of dr. Then the work done should be dW it is equal F into dr. From W it is equal F into S, force into displacement. So we need to move the point A, which is from the O point to R distance. Okay, we need to move dr distance. The work done should be dW is equal F into dr. Okay, now we have to integrate on both sides. For getting total work done. Okay. Therefore, integral of dW it is equal to capital W. It is equal integral of F into dr. So here the work done should be negative in nature. Negative force should be acting because of the intensity of electric field direction. It is here the displacement of the charge. It is opposite direction. So here this is the intensity of electric field and it is the dr. So the work done should be negative. So here minus F into dr from where to where? Infinitive to R. So here F is already you know that, where what is that, F is equal to 1 by 4 pi epsilon naught Q naught by what is that? Q naught by X square. Q naught by X square. Okay. X square, it is nothing but dx. Here it is dx, it is the where F into dx. So we need to displace the x distance will be participated into the dx. Okay, f into dx. Where it is, we have to integrate the 1 by 4 pi epsilon naught into q naught by 4 pi epsilon naught integral of, this is infinity to r, and here infinity to r, 1 by x square dx here, 1 by x square dx. The integration of 1 by x square dx, it is equal x power minus 2 dx, integral of x power minus 2 dx. It will be equal to x to the power minus 2 plus 1 by minus 2 plus 1. It is equal to x power minus 1 by minus 1. It is equal to minus of 1 by x here. X inverse is equal to 1 by x, minus it is equal to minus 1 by x. So here the integration should be, we can get minus of q naught by 4 pi epsilon naught integral of infinity to r. So directly we have to write that is integral of, it is 1 by minus 1 by x infinity to r. Okay, the integration of 1 by x square dx, it is equal to minus 1 by x. So these are the limits. Now we have to apply the limits. Upper limit minus lower limit. Upper limit is the r value and lower limit is the infinity value. Okay, let us see how we can get. So this is the capital W, the total work done to move into the r distance. Let us see. So here, that is nothing but, from this we can write W, it is equal minus into minus, it is the plus value, it is q naught by, what is that, 4 pi epsilon naught. It is equal upper limit 1 by r minus lower limit 1 by infinity. Okay, where x replacing by r minus of x replacing by infinity. It is equal 1 by 4 pi epsilon naught q naught by, what is that, r. It is equal minus 1 by 4 pi epsilon naught q naught by infinity. Something by infinity is equal to 0. Directly we can write that it is equal, since here we need to write 1 by infinity is equal 0. Okay, so this is the W, whereas the q naught, we have to work done to bringing the charge from the infinity distance is the q naught charge, that is W by q naught. This q naught will be came this side, 1 by 4 pi epsilon naught q by r here. So what is W by q naught? Already we wrote that. The definition from the potential, already we write that V is equal to W by q naught. Okay, so W by q naught, it is equal to V here. V is equal to 1 by 4 pi epsilon naught q by r. So this is the intensity of the intensity of the electric potential. So this is the electric potential where V is equal to 1 by 4 pi epsilon naught q by r. So electric potential on a point charge. So electric potential on a point charge, it is equal, V is equal 1 by 4 pi epsilon q by r. So this is the derivation. You have to find the potential on a point charge. Okay, clear? The work done to bringing the positive charge, the work done to bringing the positive charge from infinitive distance, distance into an electric field is stored in the form of electric potential energy, electric potential energy, electric potential energy. So that is the U. So here the work done to bringing the positive charge from infinitive distance into an electric field. So that work done it is equal, how much the work done it is, V into Q, because of, since V is equal to W by Q or Q naught. So V into Q naught. Hence this is in the form of electric potential, stored in the form of electric potential energy. So the electric potential energy U is equal to, you can write that V Q naught. Already you know that V is equal to 1 by 4 pi epsilon naught Q by R into Q naught. Say therefore potential energy U is equal to 1 by 4 pi epsilon naught Q naught by R. So this is the electric potential energy of a point charge. Okay, clear? And electric potential V is equal to 1 by 4 pi epsilon naught Q by R here. Okay, this is the potential. And electric field E is equal to 1 by 4 pi epsilon naught Q by R square. This is the electric field, intensity of electric field. And force acting between two charges F is equal to 1 by 4 pi epsilon naught Q naught by R square. Q naught by R square. So there are slight differences are there. Here there is only Q, here there is Q naught. Here only Q, here there is Q naught. That is the variation. Okay. So simply you have to remember, this is the intensity of electric field, this is the force acting. So force acting between two charges F by Q naught is equal to E. Simple. F by Q naught. Some F by Q naught cancel, remaining it is the E. Okay. U is equal V Q naught. V is equal 1 by 4 pi epsilon naught into Q by R into Q naught. It is the U. Clear? So this is the electric potential energy. This is the electric potential, intensity of electric field, force acting between two charges. Right. Let's see. Electric potential energy of an electric dipole placed in a uniform electric field. So we have to find the electric potential energy of an electric dipole which is placed in a uniform electric field. So now let us, so this is the uniform electric field, let it be here. Uniform electric field means the intensity of electric field acts at any point is same. So that is the uniform electric field here. So this is the direction of the electric field, uniform electric field. So there is an electric dipole. So here there is an electric dipole. The electric dipole, it is nothing but if two equal and opposite charges, so this is minus Q and this is plus Q. Two equal and opposite charges, quantity magnitudes are equal but the sign it is the opposite to each other. If two equal and opposite charges are separated in a small distance, that is 2a distance. How much distance it is? 2a distance. That is 2a distance. This arrangement is known as the electric dipole. Whenever we have to put an electric dipole into the uniform electric field, so then the force should be acting on here, that is the F is equal to EQ. F is equal to EQ in upward direction. And also in downward direction, the force acting on the minus Q charge F is equal EQ. The force is equal but opposite direction because of the charges are different. Okay, equal and opposite charges will be equal and opposite forces should be acting. The net force on the dipole is equal to the EQ and plus minus EQ, and therefore it is equal, net force, it is equal 0. So whenever the equal and opposite forces should be acting on the same object, then it will be rotating with some angle. So here the rotation should be, what is nothing but, with the angle they can be, the dipole should be rotated with some angle, that is theta, that should be called as torque. So the torque, it is tau. Okay, so here the work done should be, it is equal to torque into d theta, tau d theta. So how much torque should be acting here? The torque, it is equal any other force into perpendicular distance here, right? So this is the perpendicular distance. This force should be acting in this direction. This force should be acting in this direction. What is the perpendicular distance here? This is the perpendicular distance. Any other force, of course it is EQ, but plus EQ minus EQ. Any other force into perpendicular distance. This perpendicular distance, already we derived that the torque, it is equal PE sin theta. PE sin theta. Let it be dW here, integrates the total work done here. dW, it is equal integral of tau d theta from theta 1 to theta 2. From theta 1 to theta 2 here. So we need to integrate here. It is integral of tau means PE sin theta. Okay, d theta, theta 1 to theta 2. It is equal PE integral sin theta d theta. So integral of sin theta d theta, it is equal minus cos theta, theta 1 to theta 2. Now we have to applying the limitations. This is the work done, capital work done here. Okay, this work done should be stored in the form of electric potential energy. Already we derived it. So therefore U is equal to, what is that? PE. So minus negative sign should be here, minus PE into, we have upper limit minus lower limit. We can change the lower and upper, then minus should be cancelled out here. Okay. So here cos theta 1 minus cos theta 2. So along with this direction, it is the cos theta, that is positive sign. Along with this direction, it is the minus cos theta. Okay, right. So therefore here this is the electric potential energy of an electric dipole, which is in the uniform electric field. Okay, so this is the equation. Electric potential of a dipole at an axial point. Okay, right. What is meant by axial line here? Axial point or axial line, the line which is joining two charges of a dipole. So this is a dipole having positive and negative charges, equal and opposite charge. This is negative charge and this is positive charge here, which is 2a distance between them, 2a distance. This is the center of the dipole having a and a distance. Okay, now we have to find a point which is on the axial point. So this is the line at point P. We have to find the potential here. V is equal to how much? Okay, the point P is the distance from the point O, that is the R distance. Okay, so here this is the point A and point B. Minus Q is at point A, plus Q is at point B. So now the potential should be acting by two types. Here the potential should be acting by positive charge on the point P and the negative by the negative charge on the point P. So by the positive charge and by the negative charge there may be a chance to acting the electric potential, right? So here from the by the point Q charge is acting on the point P, then the potential should be here. The basic potential equation, it is V is equal to 1 by 4 pi epsilon naught Q by R here. So this is the potential acting on a point charge. So now let us find by the plus Q charge there may be a distance B to P. So BP is equal, you can write that. What is that here? OP is already know that R and OB is already know that A. So BP is equal OP minus OB. OP is equal to R and OB is equal to A. R minus A is equal to BP. Clear? And similarly, the potential acting by the minus Q charge on the point P, then from distance A to P is equal, AP is equal, how we can write that? OA, AO plus OP. So AO is equal to small a and OP is equal to already R plus A. So these are the points you have to remember here. Right? Let us see. Potential acting acts by positive Q charge on point P is V1 is equal to 1 by 4 pi epsilon naught Q by what is that? BP. From distance it is equal to BP. BP is equal to already you know that 1 by 4 pi epsilon naught Q by BP is equal to R minus A. R minus A. This is equation 1. Okay. And similarly, potential acts by negative charge on point P, V2 is equal to 1 by 4 pi epsilon naught Q by that is AP, because of the distance between minus Q and P is equal to AP. It can be written as 1 by 4 pi epsilon naught Q by AP is nothing but R plus A. R plus A here. Here the charge is negative and you put the negative sign. This is equation 2. From 1 and 2, the net potential you can write that V net is equal V1 plus V2 here. Here V1 is equal to 1 by 4 pi epsilon naught Q by R minus A. This is R minus A and minus of, because of the V2 is equal negative sign, minus of 1 by 4 pi epsilon naught Q by what is that? R plus A. So just simplify here. How we can simplify that? It is V is equal to 1 Q by 4 pi epsilon naught is common, and here 1 by R minus A minus 1 by R plus A. Okay. Let us write here. What is that? A plus B into A minus B. It is 4 pi epsilon naught. A plus B into A minus B, it is equal to A square minus B square. A square minus B square. Here that is equal to R plus A minus of R minus A. Okay. And it is equal to Q by 4 pi epsilon naught is equal to R plus A minus R plus A by R square minus A square here. Minus R plus R will be cancelled out. A plus A to A. So this is the V here. So from this we can write V is equal Q by 4 pi epsilon naught 2a by r square minus a square here. But we know that the momentum, dipole momentum P is equal to 2aq. So this is the dipole momentum, dipole moment. So let us 2aq is replacing by P. Okay. So therefore we can write that V is equal to 1 by 4 pi epsilon naught P by r square minus a square, r square minus a square. This is the electric potential acting on the point P at any axial point of a dipole. So here one more thing it is, if r is very much greater than a, so this is the a value, r is very much greater than a. So because of we need to assume the point is which is outside of the distance between dipole. It is an axial line. So hence it will be r will be always more than to the greater than to the a value. Hence a will neglect. A will neglects. So if a will be neglects, then the equation should be, you have to write here, what is that? V is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught q by p by what is that? R square, p by r square. So this is the electric potential at any axial point. Electric potential at an axial point, P by r square, 1 by 4 pi epsilon naught P by r square. Now let us find electric potential of a dipole at an equatorial line, equatorial point. Okay. And before that we have to derive from at an axial line, but now we have to derive at equatorial point. So the equatorial point, it is the line which divides two parts of an axial line. So this is the axial line of a dipole. This is the minus q charge and this is the plus q charge. This is located at point A and this is point B. This is the center of the dipole. From this point, this is the equatorial line. Equatorial, this is the center point. The distance, it is the here 2a distance. Here this is a and this is a. Okay. And now a point is, let us assume P. So here there is a potential should be acting by the negative charge and there is a potential should be acting by the positive charge. Okay. So here the potential should be acting by the negative charge, it is V1 and it is V2. For example, it is V2, it is V1. The V net is equal, the potential by the U net is equal. So here you have to, the point assumption from O to P, it is equal to R. O to P is equal to R. Okay. Here, what is that we have to write? Potential acts by positive charge on point P. V1 is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught q by, what is that? By positive charge, it is BP. It is BP. So from this triangle, we have to measure the BP value. It is equal side square plus side square. So here BP is equal, BP square is equal OB square plus OP square. It is equal R square plus A square. BP square is equal. We need to find BP. It is equal under root of R square plus A square here. Therefore, we can write that where Bp is equal, V1 is equal to 1 by 4 pi epsilon naught Q by root of, it is R square plus A square whole power 1 by 2. The square root should be written as 1 by 2. This is equation 1. Next, potential acts by negative charge on P, on point P. That is V2 is equal to 1 by 4 pi epsilon naught Q by, what is that? Minus Q, it is equal to AP here. So from this AP is equal to, you can write that, what is AP here? Side square plus side square, and AP is also under root of R square plus A square here, because of same distance are there. So then it is minus 1 by 4 pi epsilon naught Q by R square plus A square whole power 1 by 2. This is equation 2. The net potential acts on the point P, it is equal to V1 plus V2. Here V1 is equal to 1 by 4 pi epsilon naught Q by R square plus A square whole power 1 by 2. And plus into minus of, plus into minus is minus 1 by 4 pi epsilon naught Q by R square plus A square whole power 1 by 2. Right? So these two are same. This value and this value is same. Let cancel. That is equal 0. So the net potential acting on the equatorial line of a dipole, okay, at an equatorial point, the potential should be here. How much here it is? 0. The net potential is equal to 0. But in case of axial line, the net potential at an axial line is equal to 1 by 4 pi epsilon naught P by what is that? R square. So this is at axial line, but an equatorial line, the potential is equal to 0. The net potential is equal to 0. Okay? Right? So the potential at any point is also there. The potential at either is not at the axial point or not at equatorial point, but where the point it is, somewhere whatever it is. For example, this is a dipole. The point it is not here and the point is not here, but except assume that this is a point. So here we need to find, at this point the potential V is equal to 1 by 4 pi epsilon naught P cos theta by R square. P cos theta by R square. So this is the potential at any point. So this was already derived by me. I will be given in our iCards. You have to see once and follow it. Okay. So from this we can say that if there is an axial line, the theta will be 0. Because of there is no angle. If there is an axial line, if point P is at an axial line, the theta is equal to 0. So if theta is equal to 0, then cos 0 is equal to 1. Then we can write that is axial line. V axial line is equal 1 by 4 pi epsilon naught P by R square. P by R square, which we are derived already. If there is at an equatorial line, here the theta is equal to 90 degrees, where cos 90 is equal to 0. Something into 0 is equal to 0. That is the V equatorial. Okay. So this was already derived by me, and I have to provide in our iCards. You have to check it and follow it. Okay. So this is the complete information about the electric potential. So in this video we are discussing the electric potential at a point charge, and electric potential energy, and electric potential energy of a dipole which is kept in a uniform electric field, and also electric potential at an axial point of a dipole, and electric potential at a equatorial point of a dipole and also electric potential at any point on the dipole. So these are very important for basics of the NEET and IIT, and these are the important for the board examinations. Okay, so